Hey, Algebra 2 Honors. We are continuing on today with Unit 6, Day 2. And today we're going to talk about factoring techniques with cubic terms. So if you take out some paper, we're going to take some notes by hand, and we're going to deal with techniques involving perfect cubes. So to get started here, you can see we have a quick multiply example. And I'd recommend hitting pause real quick, just confirming, can you get the correct product for multiplying those two quantities together, a binomial times a trinomial. Okay, this is something we actually did again at the very beginning of the year when we talked about some initial factoring techniques and also multiplying of polynomials. So while you're getting yourself all situated there, I'm going to start writing my product out. So let's see if we have a binomial times a trinomial. I'll put the trinomial across the top and I'll do some box method here. And then I'll put the binomial on the side here. So x times x squared is x cubed. Then x times 3x is 3x squared. And then 9x in the last spot. Take -3, multiply by everything. So -3x squared minus 9x and then minus 27. And you'll notice that we get these kind of nice diagonal patterns of terms that are like terms that we can combine. So in the end, what's kind of unique is, oh wait, 3x squared and -3x squared cancel. 9x and -9x cancel. So the product of x minus 3 times x squared plus 3x plus 9 equals x to the third minus 27. Okay. So what we know is that this right here is the factored form of this expression on this side, right? When something's written as a product as opposed to two terms being subtracted, this right now is the factored form of x to the third minus 27. And if we look at x to the third minus 27, what we're taking there is it's the difference of two terms that are both perfect cubes, right? X to the third, definitely a perfect cube, but so is 27. It's 3 times 3 times 3. So when practicing with our new pattern here, here's what we're going to start getting something to look like. Maybe not what we expected necessarily, but when you factor with perfect cubes, it's always a binomial times a trinomial. And right now, let's talk about what that general pattern looks like when factoring with the difference of perfect cubes. Okay, so the general pattern. Okay, is the following. So we've got x to the third minus y to the third, and that would equal x minus y, so it's going to be that binomial first, times x squared plus xy plus y squared. Okay. So how do we develop this general pattern? The main idea is that the binomial is the cube root of each of these. And we should be really good at cube roots based on what we just did in Unit 5. So that's where x and y come from. And the trinomial that follows is based off of what we wrote in the binomial. So if I square x, that's the first term of the trinomial. If I multiply these together, x times y, that's the middle term here. And then finally, take the second term of the binomial and square it to get y squared. And although this looks like a more involved and intense problem than, let's say, difference of perfect squares, it's something that you'll get used to and you'll become very good at once you get a little bit more practice. As a quick thing to help us remember the pattern here, I'm going to use the acronym KCA as a way to remember these signs. So we're going to always keep the sign in the binomial, which means that if I'm subtracting, that this becomes subtraction here. Then you're going to change the sign in the middle of the trinomial. So if it was negative here, we change it to positive over here. And then what does A stand for at the end? A means you always add that last term of the trinomial. So if you remember the acronym keep, change, add, that's a good way to remember what the signs are that go into those locations, because it's always going to be the same sign format. All right, let's do some practice. So for practice, we'll start with a cubed minus 64. All right, so those are both perfect cubes, right? A cubed definitely makes sense. 64 is 4 cubed. And knowing that helps me to get that binomial first, right? So it would be a minus 4 to start. That's the cube root of each of these. Times, then we're going to multiply by a trinomial. So how do I get that? Well, square the first term from the binomial. So that's a squared. Change that sign to plus. A times 4 is just 4a in the middle. And then finally, at the end, we're going to add whatever 4 squared is, which is 16. And of course, we can check any of these by multiplying everything back together again. Okay, but for now, hopefully you'll trust me that, yep, that multiplied out would give you a cubed minus 64. All right, how about 8y cubed minus 27? Okay, so 8y to the third minus 27. These are both perfect cubes. Remember, 8 is 2 cubed. 27 we saw earlier is 3 cubed. So this would start off as 2y minus 3. That's the cube root of each of these terms, and that's what your binomial should look like. Okay. For your trinomial, we're going to square the 2y to start. So 2y, that quantity squared, is 4y squared. Don't forget to square the coefficient. Change to plus in the middle. 3 times 2 is going to give you a 6y in the middle when I multiply those together. And finally, plus 3 squared, which is 9. And if you're getting used to the pattern, you can at any point along the practice here, you can stop and just try and give some of these a shot on your own here. So what about 125 minus x cubed? 125 a perfect cube? Sure is, right? It's 5 to the third power. So when I take the cube root of each of these, the first binomial would be 5 minus x. Okay. So we'll start with 5 minus x, and then from there, square this first term. And don't just reverse the order because you like when x comes first, by the way. You got to leave it in the order of if the 125 came first, the 5 has to be first over here. Okay, so that's going to be 25 plus, multiply these for the middle, 5x plus square the x to get x squared. Okay. All right, looks like we're doing a pretty good job here. Maybe we'll just do a couple more for practice. If I gave you 1000 x squared minus 36 y squared. Okay. Taking a look at this one. I think I maybe meant to make this 100. Sorry, guys, not 1000. I was trying to throw you off a little bit on your game here because if we're thinking about these patterns with perfect cubes, just be aware if I throw in a perfect square at you along the way. So this is actually difference of perfect squares, but of course I messed it up along the way. Oops. Okay. So the pattern for perfect squares is take the square root of each, and one gets separated with plus, one gets separated with minus. So hopefully you're okay recognizing when that pattern exists versus the pattern with perfect cubes. Okay, let's try one more, and these will be perfect cubes. Okay, a to the 6th minus b to the 15th. When the exponents get larger than just having x cubed or y cubed, we know that they're perfect cubes based on what we did in the last unit if they are divisible by 3. And since both of these are divisible by 3, we can take the cube root by saying that the first binomial would be a squared minus b to the 5th. Okay, that's the cube root of each of those. So then the trinomial is square a squared, so that's a to the 4th, plus middle multiply, just a squared b to the 5th. And when you square b to the 5th, if you're not sure what that becomes, just do b to the 5th times another b to the 5th in your head to get b to the 10th. So sometimes larger exponents than 3 do get a little bit tough for us to work with, but once you get used to it, again, it's just like all of the other patterns that we've done all along. Okay, so we know two kind of major patterns. We know x squared minus y squared is this, x plus y times x minus y. What about x squared plus y squared? So we have a difference of perfect squares. Do we have a sum of perfect squares technique? And the answer to that would be no, we do not. And we now know the pattern for x cubed minus y cubed. X minus y times x squared plus xy plus y squared. Well, get something ready for something really cool. Because not only do we have the difference of perfect cubes, but even though it didn't work for perfect squares, we have a pattern for x cubed plus y cubed. Okay, so difference of perfect cubes has a pattern, so does the sum of perfect cubes. And it just so happens that it's a really similar pattern to x cubed minus y cubed, which is good news. So we don't have a lot to change. The first binomial is still the cube root of each of these, but now it's x plus y, so no surprises there. And then the trinomial is still based off of this binomial. It's going to be x squared minus xy in the middle, and then plus y squared at the end. So if you remember from earlier, I said, oh yeah, we have that keep, change, add rule, right? So we keep the plus sign, change the negative there, and then add the last term. You know, that whole idea still holds true. We're keeping the plus sign, change in the middle to a negative, and then add at the end. So we'll do a little bit of practice with this. And then we have one more technique that we'll kind of just start briefly today, but pick up on it more tomorrow too. Okay, so let's try x cubed plus 216 and see if we can factor that. So using this technique with sum of perfect cubes, the first binomial is x plus 6. Okay, 6 to the third is what 216 is. So then the trinomial would be x squared. Now we got to change this middle sign to minus, and 6 times x is just 6x. We're always adding at the end, so plus 6 squared, which is 36. All right, let's just do a couple of more. We'll do number 2 is 27a cubed plus 64. And these numbers are going to start getting really familiar, right? I mean, there's only so many perfect cubes we can really work with here. So if we have 27 and 64, that's 3 cubed, that's 4 cubed. So the binomial, sorry, would be 3a plus 4 to start, 3a plus 4. And then from there we have the trinomial, so square this first term to get 9a squared. Minus, now just careful in the middle, 3a times 4. Don't write 3a times 4 in the middle, like actually multiply those together to tell me that that's 12a. Okay, don't leave me hanging there. So you can write 3a times 4, but then multiply those to get 12a. And then at the end, plus 16, 4 squared, and we're good to go. All right, one more of these. We'll do x plus y cubed quantity plus 8. So when you have a quantity cubed, of course, that's a perfect cube. We already know that 8 is a perfect cube because it's 2 cubed. So based on all that, I think that the only thing I would recommend in this one is, of course, using a dummy variable. Some of you might be able to visualize the factoring without using a dummy variable, but I think it really does help. So what does this turn into then? A cubed plus 8. So a cubed plus 8 would factor into a plus 2 times a squared minus 2a plus 4. And then for the last and final part of this process is, of course, wherever we see an a, which is in a lot of places, we have to replace it with x plus y. So we're going to get x plus y plus 2. And then you're going to get x plus y quantity squared. Make sure you square that whole thing. Minus 2 times the quantity, x plus y, plus 4. And that's really the final answer here. Okay. So you don't have to square the x plus y. You don't have to worry about distributing the -2. This is a factored answer still, right? It's written as a product. But in the end, you have to remember to carefully sub in that value for a from the dummy variable substitution that we made. Okay, last but not least, the last thing we're going to talk about in this lesson is something called factoring by grouping. And just a really quick introduction into factoring by grouping, because our next lesson is all about factoring by grouping. Usually factoring by grouping has 4 or more terms. Okay, so we use grouping techniques. We usually see a polynomial that has, or an expression that has 4 or more terms. So for example, if I gave you MA plus MB, plus an plus bn. Okay, we definitely have 4 distinct terms. They're all being added currently. To factor by grouping, there's a couple different techniques that we might want to try. But in this scenario, I'm going to group the first 2 terms together and then the second 2 terms together. And what we'll see is if I group the first 2 terms together, that I can take out a GCF of m. And that leaves me with the quantity a plus b. And then I'm going to carry down the plus sign. From the second group, I can take out an n, and that also leaves me with a plus b. So rather than using a dummy variable here to replace a plus b, maybe you're okay that if I look at this as one whole term, plus this is another whole term, that they both have a plus b in common. And what that means is if I take out a plus b as a GCF, what does that leave me with from the first group? M. Okay, so open up a parentheses because we're taking out a GCF. So we're going to multiply by m there, plus if I take a plus b out from the second group, I'm left with n. And notice how we took something that was adding 4 terms together and wrote it as this product. And I bet you anything that if we were to multiply all this out again, box method or FOIL, we're going to get that same thing that we started with. So grouping is actually a really important technique depending on the scenario to be able to factor and break something down. Okay, so the next one, let's take a look at 6xy plus 4x plus 3y plus 2. Okay, so for this one, is the grouping always going to be 2 and 2? Not necessarily. But that's usually what I default to start, okay? So if I group the first 2 together, is there a GCF I can factor out? And it turns out I can take out a 2 from the coefficients, and I can also take out an x. So if I take out a 2x, that leaves me with 3y plus, take 2x from here, you get just 2 left over. Plus, what would I take as a GCF from the second group? Well, the second group doesn't really have a GCF, does it? But I think it would help you if I wrote it like this. What if I took out a GCF of 1? Pretty unexciting GCF there. But when I write it as 1 times the quantity 3y plus 2, now I can see how that 3y plus 2 is a GCF, right? It's a GCF for this and for this. So if I take out 3y plus 2 on the outside, that leaves me with 2x from the first group plus just a 1 from the second group. And I may not always write it in this format where I take out a 1, but that really helps to remind me that in the end I need a plus 1 in that location. We're going to do one more, okay, a really good one to finish. How about x cubed plus x squared minus 4x and then minus 4. Okay, so when we see these 4 terms, we might consider factoring by grouping, which we'll look at the first group and the second group there. From the first group, I can take out x squared. That leaves me with x plus 1. From the second group, I can take out negative 4. And why do I really want to take the negative with that 4? Because look at what it leaves you with. X plus 1, right? Think of dividing each of these by negative 4. You'll get x plus 1 left over. And that's really the whole goal. You, in the end, want to have these 2 quantities match when you take out those GCFs. So now that they both have x plus 1 in common, when I write that on the outside as my GCF, what am I left with from the first group? Just x squared. Minus, when I take that from the second group, I'm left with minus 4. And this is now factored. However, before you shut off the video here, is it completely factored? The answer is no, because this is difference of 2 perfect squares. So the cool thing is that even though it looks like we're done, we get to break that down even just one more step, just a little bit further. And now this is in a completely factored form. And there's a lot of advantage to being able to write a polynomial in a completely factored form. And we're going to explore that more in the next few units. But for now, we'll stop there and say this is factored and we're good to go. So you learned a lot of cool things in this lesson. You know some new techniques with factoring with perfect cubes. And just a little taste of grouping. Grouping gets so much cooler, guys. Just wait till the next video. You'll see. All right, that's it for today. Have a good rest of